Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we started our journey with boosting algorithms, especially adaptive boosting of decision trees as a strategy to increase the performance of weak learners like decision trees by putting them together through ensembling and iteratively changing the weights of the data points as we proceed to training more and more trees. So in today's class we will continue our discussion on adaptive boosting and we will also enter the realm of gradient boosting. So let us go ahead and get started. So the topic is adaptive boosting of decision trees, and we were particularly discussing the AdaBoost algorithm which was proposed back in the year 1997. And in this algorithm which was initially developed for classification, the prediction of the boosted set of decision trees yb as a function of the feature vector x is given by the sine function of the weighted sum of the predictions over all the trees, right. So the index b is referring to the decision tree. So index of the decision trees and capital B is the total number of trees, and like I had said we are considering the sine function here SGN sinum function, not SIN sine, right. This is SGN, the sign of the operator or the sign of the number or the sinum function, and that is because the classes, right, the true classes of each data point they are taken to be either -1 or +1. So this is the true class of the ith data point, and we also discussed that the sign SGN of y is basically +1 if y is greater than or equal to 0, that is how we are defining it, and it is -1 if y is less than 0, and this is done because there are only two classes, right, class 1 which is -1 and class 2 which is +1. So if that makes sense, we had also discussed how the alpha b, right, the weight of each point in or the weight of each decision tree is decided, right, and basically we were weighting those trees more which are more accurate and weighting those trees less which are less accurate, right. So alpha b was equal to log of 1 over epsilon b minus 1, and alpha b is the weight of the bth tree and epsilon b is a weighted loss function or a normalized loss function. Now in the last class we did not discuss how this epsilon b is computed, so that is what we will do here now. But you can already see that if epsilon b is large, if the error is large, alpha b will be low, the weight will be low, and if epsilon b is low, the error is low, alpha b will be large or the weight will be large. So now how is the normalized weight function defined? So epsilon b is defined as some I going from 1 to n, the weight assigned to the ith point in the bth tree times the loss due to the ith point in the bth tree, and just normalized by all the weights added together, right. So this WIB here is the weight assigned to the ith point in the bth tree, and this is also something that we are going to adapt, right. Remember, the whole idea of adaptive boosting is that the points which are incorrectly predicted, you increase their weight in the future trees, so that the model is forced to learn how to predict them well, right. And this LIB is the loss function of a single point I from the prediction made from the bth tree. Okay. So, I hope this makes sense, and then this LIB, right, is further defined as the indicator function of the predicted value of the ith data point not being equal to the true class, right. You remember we had said that the true class can be either class 1 which is -1 or class 2 which is +1, and here we are just looking at the indicator function, right, of the predicted value not being equal to the true value. If it is not equal, then we will get a 1. So, the loss function will be 1 if the prediction is incorrect, and if the prediction is correct, the loss function value will be 0. So, I hope this makes sense, right. So, this is the indicator function, right. So, essentially this is equal to +1 if YB, right, the predicted value of the bth tree is not equal to the true value, and is 0 if the prediction is correct, right. So, this corresponds to the correct prediction, and what happens above corresponds to the incorrect prediction where the loss is higher, it is equal to +1. Okay. So, now that we know how the normalized weight function is defined, we can discuss how these weights are decided, right. These weights which have to be changed as the training procedure goes on and on and on. Alright. So, the weight function now is defined as follows. It is equal to, right, at the beginning of the algorithm for the first tree, all the points are given equal weightage, right, because there is no reason to suspect that any specific point will not be predicted properly. So, for all the points equal weight is assigned. So, this is for the first tree, all points have equal weight. And that is because, like I said, there is no reason to suspect that any given point will be predicted incorrectly. But after this is where the magic of AdaBoost starts, that as you go to further and further trees, you try to increase the weight for those points that are incorrectly predicted. So, how is that done? This is done as follows. So, the weights are updated in a new tree using the following equation. So, Wi, right, weight of the ith point in the b plus 1th tree is the previous weight multiplied by the exponential of alpha b, right, the weight of the tree times the loss function, right. So, if you remember, this was the weight of the bth tree, and this is the loss function of the ith point in the bth tree. Okay. And this exponential function is where, right, all the magic is happening, that the points which are incorrectly predicted, they are going to get boosted, right, their errors are high. So, we need to force the model to look more closely at those points. Okay. So, how does this happen? Let's go ahead and understand that. Okay. So, if for example, this epsilon b, right, let us look at what will happen here. So, if alpha b is greater than 0, right, then 1 minus epsilon b minus 1, right. So, that has to be greater than 1. Remember that alpha b is log of 1 divided by epsilon b minus 1. So, if alpha b has to be greater than 0, right, this constant here, then you need 1 minus epsilon b minus 1 to be greater than 1, because alpha b is log of this quantity, and a log of a quantity can be greater than 0 only if the quantity itself is greater than 1, right. So, for alpha b greater than 0, this means that 1 over epsilon b should be greater than 2, which means that your epsilon b should be less than half. Okay. So, if epsilon b is less than half, your alpha b is positive. That means that if the loss function is high, right, is plus 1, then the weight will increase, right. So, in this scenario, right, the weight function WIB plus 1 will be greater than WIB if LIB is equal to 1. So, if the point is incorrectly predicted, your weight is going to go up, right, as long as alpha b, right, here is positive, and alpha b will be positive if epsilon b is less than half. So, that means that the error, right, made by the bth tree should be less for the weights to increase, right. For the weights to increase, the error made by the bth tree should be less than half. Now, what happens if the converse is true? Somehow, let us say your tree is not as accurate, right, if epsilon b is greater than half, then actually the boosting procedure will fail. So, on the contrary, if epsilon b is greater than 1/2, then your alpha b will be less than 0, so that your weights, right, will start coming down. WIB plus 1 will be less than WIB, right, which is problematic, right. You wanted the weights to actually go up when the points were incorrectly predicted, but instead the weight will actually come down if the tree was bad to begin with, right. So, therefore, for AdaBoost to work effectively, we already need to have a classifier that is better than random guessing, right. So, the initial decision tree, right, must be better than a random guess. Right, that is when, right, when this happens, your epsilon b will be less than 0.5, right, that is what was needed here, and if epsilon b is less than 0.5, you will see that alpha b is greater than 0, and if alpha b is greater than 0, WIB plus 1 will be greater than WIB if LIB is equal to 1. Now, what does this mean? This means that for incorrect points, right, incorrect points means LIB is equal to 1. For these kind of incorrect points, your weight will go up, which is what was the entire premise of adaptive boosting. Okay. So, now this completes the discussion of the AdaBoost algorithm, and although we have primarily discussed AdaBoost as a classifier, it has also been extended to regression problems where the prediction is given by the weighted median of the trees. Okay. So, that is something you can look up if you are really interested in. So, AdaBoost has also been adapted for regression problems. Okay. So, now what we will do is we will change gears. Okay. So far we have been looking at adaptive boosting. but there is another type of boosting that exists, and this is called gradient boosting. Okay. So, we will now start with gradient boosting, wherein the gradient of the loss function is used, right, to improve the performance of the decision trees. So, gradient boosting of decision trees, that is the next concept. Okay. So, what happens in gradient boosting? So, in gradient boosting, like I mentioned, each successive tree in the ensemble of trees is trained to correct the errors made in the prediction of the target variable by the previous tree. Okay, so that is what is happening. Unlike adaptive boosting, where you are trying to increase the weight of the subsequent points, here what we are doing is we are not increasing the weights of the subsequent points, but rather we are trying to train each new tree to correct the error made in the prediction of the previous tree. Okay, and that all makes sense, but why is this called gradient boosting? So, let us try to understand that using the example of a loss function. Okay. So, if we denote the prediction of the bth tree as fb of x, the error in predicting point I, right, is the residual, basically is called the residual. So, let us denote that as R. So, RB of point xi is basically the difference in the true value and what the tree has predicted, right, the bth tree. So, this here is the residual, this is the true value, and this here is the predicted value. Okay. So, this is all good. So, now if you wanted the true value, then you can write that as the predicted value plus the residual. Okay. So, if you have to fix the prediction that is made by the previous tree, then you can add the residual to it and you should get the right answer. So, in a sense, the residual is basically the error made by the previous tree. So, that is the error that we are trying to capture here in gradient boosting. So, can we obtain this error somehow? Okay, how do we obtain this error? So, let us consider the simple case of the sum of squared errors. So, considering the sum of squared errors SSE loss function, okay, the loss is basically sum I going from 1 to n, the true value yi minus f hat b xi whole square, right. So, this is very familiar to us, that is the loss function. Now, let us try to figure out what the error is, right. So, we already discussed that this is the error, right, yi minus f hat b xi, and that's basically rb of xi, right. That's exactly equal to rb of xi. So one could also write that this as sum I going from 1 to n rb xi whole square. Okay. So now how do we get this residual, right? Is there a way to obtain this residual from the loss function? Okay. Now something very interesting emerges if you take a derivative of this loss function versus f. Okay. So if you take that derivative del lb by del f hat b xi, then that essentially becomes, this summation goes away and what just remains is the ith data point, right. So 2 times yi minus f hat b xi times the derivative of whatever is inside the parenthesis with respect to f hat b, and that is simply minus 1, right, because yi is a constant. If you differentiate that with respect to f hat b, you get nothing, and then if you differentiate the second term with respect to f hat b, you get a minus 1. So this is a really nice expression. So this is just minus 2 times yi minus f hat b xi, right. So this is extremely insightful, because what this means is that the residual, right, rb of xi, which is yi minus f hat b xi, that is simply equal to minus 1/2 del lb by del f hat b xi. Okay. So this is very insightful, because this tells you that the gradient of the loss function is related to the residual or the error made by the model. So if you know the gradient, right, or you can predict the gradient through the use of a decision tree, then you can do wonders, right. You can fix the predictions and your supervised ML model will start to work really nicely. Okay. So that is why the name gradient boosting comes, because the gradient has the relationship with the residual, and we are going to train decision trees, subsequent decision trees, to predict the gradient of the loss function and thus correct the wrong predictions. So therefore each new tree can be trained on the gradient of the loss function to predict the required correction to improve the prediction of the previous tree. Okay. So that is the main crux of gradient boosting. Okay. So how do we do this mathematically? So mathematically we formulate this as follows. What you do is that the prediction f hat of x of the gradient boosted decision tree is basically a constant value plus some improvements that each tree has to offer. Okay. So this is what we are doing here. Like I said, the first term is a constant and the next terms are the improvements in the prediction. So this is a constant value and this is the corrections made by successive trees. Okay. So what is the constant value? That is one question, and how do we obtain these corrections which are made by the successive trees? That is the question that we need to answer, right. So now we know how what the logic is behind gradient boosting. So all that needs to be done is to figure out, right, the constant value that you assume at the beginning of gradient boosting, and then the corrections that are made by the subsequent tree. So first let us try to find out this constant value. So in this case, and again taking the example of the sum of squared errors loss function, we are trying to calculate the constant f naught hat, right, and f naught hat is a constant. So in this case, if you want to minimize the loss function, which is here the sum of squared errors, so that is sum I going from 1 to n yi minus f naught hat whole squared. Now if you want to optimize or minimize the loss function, you just take the partial derivative of the loss function versus f naught hat and set it to 0. So that becomes sum I going from 1 to n 2 times yi minus f naught hat times minus 1, right. So this has to be equal to 0, and now the values 2 and minus 1, these are all constants, they can be dropped out. So what is left is that sum I going from 1 to n yi minus f naught hat equals 0, and this can be split into two different summations. The first summation is I going from 1 to n yi, and the second summation is sum I going from 1 to n f naught hat. But because f naught hat is a constant, all this means is that sum I going from 1 to n yi is equal to n times f naught hat, which leads to a very nice expression that f naught hat is simply the mean of the true values in the training set. Okay, so this is a really nice expression. So this means that the constant value is simply the mean of the target variables in the training set. Okay, so that is great, and now the only thing that remains to complete our discussion is to figure out how we can improve, right, the predictions at every decision tree, right. There are capital B decision trees, and we want to find out how we can improve those predictions by using the concept of the residual, right, which was simply the gradient of the loss function. So the task at hand is how do we determine f hat b x, which is essentially the improvements that will be offered by every successive tree. Okay. So if you think about it, this function can be written as a minimization of the loss over various choices of f, and of course you have to aggregate the losses sum I going from 1 to n of the loss function for every point, right, and the loss function for every point will depend on the true value and the prediction that the previous tree had made, okay, plus what we are correcting it with, right. So the function, right, that we should correct it with, the optimal choice of this function is what we will use to correct the error made, right. So if you want to understand this better, this is the prediction of the previous tree, and this is the correction made by the next tree. So all we are saying is that the best possible, right, value you can take for this corrector function is right, the optimal one, and that is the tree you should obtain next. Okay. So, I hope conceptually you are able to understand what is happening here, and like I said, the small l is simply the single point loss function, the loss function for a single point. Okay. So, where do we reach now? So, now we have to write down how we can express, right, this f hat b in terms of the residuals by training the decision tree. So, let us see how that can be done. So, in gradient boosted decision trees, each correction, right. So, f b is a tree, right, it is a tree model, right. So, let the bth tree have regions RKB, then the prediction of the tree can be written as follows, right. So, you already know how you can write the prediction of a decision tree, and that is just the sum over all the regions, the constant associated with every region times an indicator function which tells you whether the point x belongs to that region or not, right. So, this is what you already know, but what we need to discuss is how do we obtain these CK hats. So, what are the weights assigned to the regions? RKB. Okay. So, that is a question which we will be answering in the next lecture. So, this brings me to the end of today's lecture. Today what we did was we discussed the concept of AdaBoost and how it increases the weights of points in successive trees to make the classifier more and more robust, and this also depended on the fact that your first tree should at least be better than a random guess, that is when the boosting really works. And after finishing our discussion of AdaBoost, we moved on to gradient boosted decision trees, wherein we saw that the error made in predicting a data point, the target variable, is simply the gradient of the loss function at that point, and this concept is harnessed in gradient boosted decision trees, wherein every new tree is trying to fix the error made by the previous tree using the gradient of the loss function. So, in the next class we will see how this can be taken forward mathematically, and we will also discuss 3 libraries, LightGBM, XGBoost and CatBoost, which are quite popular gradient boosted decision trees that can be very useful for core engineers when they model tabular data and when they want to make predictions of target variables which are tabulated. So, thank you for joining today, and I hope to see you next time.